In this video, we're going to be looking at the definition and introduction of logarithmic functions. For us to introduce logarithmic functions, we first must look at the concept of inverse functions and the definition of how an inverse function is built and or is understood. So when we look at basic functions, say y equals x squared, it has an inverse function where we have y equals the square root of x. Again, if I were to take one function and substitute it into the other, they would undo each other, and we would be left with, say, for instance, f of g of x is equal to just the original thing we plugged in. So this is the basis for inverse functions. For us to better understand how a logarithmic function is defined, we have to make sure that we fully understand inverse functions first. The concept of most of mathematics is that we introduce something, we manipulate that something, and then we talk about whether or not it's possible for us to find an inverse. Well, an exponential function, say y equals b to the x, this function has to have an inverse if we want it to behave like the rest of the mathematical functions we work with. So the idea is, how do we find the inverse function? Well, if you recall, the basis of finding inverse function is you take the x and the y value and you swap their positions. After swapping their positions, your goal is to solve for that new y equals. In this situation, solving for y equals is actually quite difficult to consider how to do so, and impossible without developing a new function. And that's what we're going to end up doing. We introduce a new operation. So we also consider the concept of how multiplication is the inverse of division and vice versa, as well as addition is the inverse of subtraction. So now we have an exponential function, and we want to know what the inverse of an exponential function is. Well, we create that new function such that it is a log function. So the inverse function is y equals log base b of x. So if I were to take this equation and solve for y, this is the new equation I would get. Some important pieces of information that we start off with the exponential function. Note that for us to have an exponential function, b has to be greater than 0 in particularly. So, and it also can't be 1. If it's equal to 1, then it's not really an exponential function. It's really just y equals 1. So if these two statements are true when it comes down to this, then that's technically true for b in this particular function. So this is the logarithmic function such that, again, we have to state that b is greater than 0 and b does not equal to 1. Another detail that actually correlates with the log function with how it's defined is that if you look back at this version of the function, if you try to plug in a negative value for this, your b, any number to the power of y, any whole number and or any number at all, you'll notice that b to the power of y, it will never spit back a negative number. This is how we define the domain of every log function. So in this case, the domain of this function is x has to be strictly greater than 0. Again, the reason for that is because if this number was negative, there's no combination of b to the power of y that will allow this number right here to end up being a negative number. So, with that being stated, we have the definition of what a log function is. So in reality, this is just a different form of this. It's really just solving this exponential equation in an inverse pattern. It's undoing this exponential into this function. So the best way that we can verify, or I wouldn't say verify, but compare the definition of these two functions is by looking at the concept of a logarithmic form. And this is the way I'm going to define these functions and help compare the two. So you'll notice in here I have y equals log base b of x. In this form, I want to understand that base b, that is the base. I also want to understand that every log, by definition, is technically equivalent to an exponent. So this y being equal to the log function, this is really the exponent that we're talking about. Then this right here is just the inside value. And keep in mind that it's log base b of x. So as a technicality, there is parentheses around this. And if I don't put parentheses around this, then the first term is the only thing in that log function. We'll look at that more later in supplemental videos. So if I try to convert this to an exponential form, again, this should make sense in the concept of how it converts. First, I start off with the base is b. the base is the thing that has the exponent on it. So then that means the exponent is going to be there on the b. And then this is equal to, well, whatever's inside. Again, this like little base here doesn't count as the inside of a log. The inside of the log is this. This is an indicator of that log. It's very much like the square root or a cube root. It's the 2 or the 3. It's the indice of that particular radical. Well, the base b value here is the indice of that log. So with that identified, and again, this is how these things compare. Notice this is your base, this is your exponent, and everything that's inside goes over here. We need to be able to allow ourselves to convert from a log function to an exponential, or vice versa. So how are we going to better understand that skill? Well, we're going to start off with, what if we were given an exponential function 2 to the 5th equals to x. Now maybe this isn't an exponential function, but an exponential expression is a better way to say it. Maybe even an exponential equation. How am I going to convert this to its logarithmic equivalent? Now it's important for us to understand that every log is equal to an exponent, which means that this right here is the exponent, this right here is the base. So I'm going to have log base 2, and when we write that base of 2, it should be as a subscript, not as a whole number. Should be a little bit lower, closer again to the underneath of that G loop. And then it's of what goes inside here. Well, before I go what's inside, the log is always equivalent to the exponent, and in this case the exponent should be 5. So 5 is equal to log base 2, in this case, of x. So this is how you convert every exponential into a logarithmic. Let's look at another example. B to the power of 3 equals to 27. In this case, again, we should know that we should be able to evaluate this value of b just like we should be able to evaluate this x. But we're not being asked to evaluate them, we're being asked to, again, rewrite them in logarithmic form. So my base is b, I have log base b. I know that every log is equivalent to an exponent. My exponent is 3 here. And then what goes inside that log? The 27. Okay, we got one more example in this form, and e to the power of y equals to 33. Now you'll notice in this case it's a lot more variable based. E, remember, is that 2.718 ... so on and so forth forever, and then in this case y is the variable. So if I want to convert an exponential into a log, it's going to be, one more time, log base e this time, because my base of the exponent is e, and then it's y. So technically it's y equals to log base e of 33. Now you'll notice again in every single case, the other side, this exponential equaling to something, the other something is what's going inside that particular log function. Now, this one right here has poor notation. There's a special version of log, very much like there's a special version of a square root. If I come back up here, you'll notice that with this square root, I didn't write the 2 in there. If I don't write the 2 for a radical, we assume that the 2 is there. The same holds true for certain log functions. For log base e, it is the same as ln of 33. Notice how I can drop e and ignore the g, replace the o and the g with an n. This is what we call the natural log. Okay, and a natural log is really just a log of base e. So this is the basic understanding of what a log function is. It is the function that's supposed to undo an exponential function. So it should be the inverse function, which means that if I write the notation, one more detail in here is that log base b of b to the power of x. If I substitute in the exponential function with a base of b, log base b of that should cancel it out. Again, that's the definition of an inverse pair of functions. F of g of x should just let me end up with x. So the same should hold true that if I have b to the power of log base b of x, again, x being inside the log function, b being the base, this should also spit back x. Now this understanding right here might take a little bit while to grasp, but the overall goal is the understanding that log base b of an exponential function with base b to the power of anything spits back that anything. And vice versa, b to the power of log base b of anything should spit back that anything. So those are your basic understandings of what a log function is, how it's developed, and how you can convert an exponential function into a logarithmic function.